Right, so now we're going to continue to chapter 5. This is still descriptive statistic, and it's a simple linear regression. So again, this is still descriptive statistic. This is still about relationships, but here we're trying to do regression. Okay. So go over the symbols. Again, we have different measures represent different symbols. So make sure you're clear with all the symbols. So for example, sample size, we use small n, right? Not big N, small n. And the population size, this is big N, right? And population standard deviation, this is a sigma. So we can find a sigma in okay. If you can't write it very well, that's fine, but make sure, it's not big sigma, it's a small sigma. So the Word and the Microsoft software, they always want to try to auto-correct something they think it's appropriate, but sometimes they messed up, right? So that's sigma. It's like a little flat 6. And the sample standard deviation symbol will be, we use small s, not a big S. But, it doesn't matter because there's no capital S in stats. That means something else. Only N, you need to be careful. And population mean, we need to use a symbol of mu represent. Right? So mu is population mean. And what does sample mean? Sample mean is X bar. So we can make X bar here as this, right? So this is X bar. And then standard normal variable, that's Z, right? Big Z or small z doesn't matter here. And correlation is a small r, okay? So it's a small r. And the regression slope. So this is, I know in the math class you use M, but here we use B1, okay? So B1. Where's subscript? Doesn't matter. I'm gonna use the equation here to build it. So B1. So that's regression slope. And the regression intercept, it's B0. So just a notation change. Instead of using M and B, we use B1 and B0. And then the probability of observing a value as extreme or more extreme than the sample you collected, that's p-value. And then type 1 error, we use a symbol of alpha. Okay, so this is alpha. And this is capital alpha. We wanted to lowercase alpha. Okay. Okay. So get familiar with the symbols as soon as you can, all right? Especially the ones we learned. So what's regression? And what's the learning objective? So learning objective is, first we need to understand what's a regression. So let's talk about regression real quick. So we learned a scatterplot and correlation last class. And we figure out there is a linear relationship exists in the data, right? So we know there is a linear relationship. Then if we want to study further, what will be the next question? Next question will be, if there is a linear relationship, can we quantify that linear relationship, right? So we know for any linear relationship is having a general form of y equal to mx plus b, right? So we use different symbols, b0 plus b1 times x. We have b0 intercept and b1 and slope. With different combination b1 and b0, you're gonna have a different line in the xy plane, right? So if we say that there is a linear relationship, can we quantify that linear relationship by finding the slope and intercept? And that process is called a regression. So regression process is basically to find the slope intercept so that you can find the linear relationship that best explain, the relationship between the two variables. So correlation and regression, they're very closely related, right? Correlation will tell us if there is a linear relationship, whether there is or not. And the regression is telling us what is that linear relationship if there is one, right? Okay. So now let's go back to learning objective. So we should be able to perform simple linear regression to find the regression equation. So you need to find the slope and intercept. Then all you need to do is put in back to the general form, y equal to b0 plus b1 times x, right? And then when you use a regression equation to describe the relationship, and as we see that, it's not gonna describe the relationship perfectly, right? So there will be some deviations. So here we use a measure to see how well the equation, the line fits the data. How well does it explain? We use a perfect line to explain all the deviations, all the variations in the data, right? So how well does it fit? So we use a measure called coefficient of determinants, okay? And this measure has a common name, and the common name is used a lot more often than the official name. It's called R square instead, right? So most of the time we use R square. That would evaluate the goodness of fit of the regression line, okay? So, and then if you have a regression equation, already found out, then for example, y equal to 3 plus 5 times x, right? So if that's the case, if I give you an x, you can predict y. If I give you y, you can predict x, right? So that's a pretty easy task. It's just some, math, algebra skills. But that's an important concept. The most important reason that we want to do regression is so that we can do predictions. We can estimate something that we don't know about. So we can make estimations, right? And then when you make predictions, you need to be aware of extrapolations. Extrapolations can be risky. So we're going to talk about what's extrapolation, right? So these are learning objectives. All right. So recall your math linear relationship you learned, y equal to mx plus b. We're going to use the same form, but we're going to change the notation. We're going to use b0 represent intercept instead of b. We're going to use b1 represent the slope instead of m. But they are exactly the same relationship, right? They have slope and intercept. So then simple linear regression is basically determining the regression slope and the regression intercept to best fit the data for the relationship between the variables, right? So when you have a slope, what does a slope mean? Rise over run, right? That's what you learn in math class, but sometimes when I ask you to interpret the slope in terms of the context words, so please, do not just use rise over run. Use specific background information using the context words to explain that, right? And then coefficients of determination, that's R square. That will indicate how well a statistical model fits the data. So in a homework or exam, the question is always phrased as, what percent of the variability in the Y or in the data is being explained by the regression equation. So anytime you see a question like that, the answer will be R squared. But of course, you need to find R squared, right? So how do you calculate R squared? Right, so let's look at a small example. And this is a study about kids' body weight with their age. So we have 16 kids in the study, age 1, 2, 3, 4, 5, up to 16, and their body weight is recorded. So then we want to study the relationship, right? So we can draw a scatter plot. Every mark on the XY plane is the kids, individuals. So we can see that there is a very, very strong positive linear relationship, right? So then can we quantify that linear relationship? So can we find the slope and the intercept for this linear relationship, right? So here we use software to get the slope intercept, and later on we're going to talk about how do we manually calculate it. So slope equal to 5.4 and intercept equal to 11.3, as given here. So then the equation will be y body weight equal to B0 11.3 plus B1 5.4 times age. So you can also write it as in the symbol, right? So y equal to 11.3 plus 5.4 times x, right? So anytime when I ask you what's the least square regression equation, please write in this form, right? And slope equal to 5.4. So if I ask you to explain the slope using the context words, this is the example how you should explain it. That means when the kid grow 1 year older, their body weight will increase by 5.4 pounds, right? So every 1 year, they will grow about 5.4 pounds. So that's slope. So then we can do predictions once the regression equation is given, right? So then can we predict someone's body weight as for 11-year-old kid? Right? So that's very reasonable, right? So if you want to predict a kid of 11-year-old, so you need to know what is this 11? Is that X or is that Y, right? Are we given X or given Y, right? So apparently 11 is age, which is X, right? So if you want to predict his body weight, Y will equal to 11.3 plus 5.4 times X, and X is 11, right? And that's some calculation involved. So we're going to calculate this very quickly. So that's 70.7 pounds. So a kid of 11-year-old will be about 70.7 pounds. That's our prediction, right? That's pretty reasonable. Then can we use the same equation to predict a person who's 60-year-old? We get another age, right? 60 years. And then what will be the body weight of that person, right? So suppose we can just calculate it without thinking much. So 60 is still X, right? But now if you do the calculation, that will be 324 after you calculate. You need to add 324. So that will be 335.3 pounds. Now the question comes. It's reasonable to say that a kid of 11-year-old is 70 pounds. But is it reasonable to say that a person who's 60 years old is 335 pounds. That doesn't sound right, right? We don't normally see a person who's over 300 pounds. So then what's going on there? We use the same equation. We make sure the calculation is correct. There's no calculation error here. So then what's the issue? What's the problem? Okay, so this is related to a term called extrapolation. So what does the extrapolation mean? So let's think about, the process we just did. So we only collect data from 1-year-old up to 16-year-old, and the trend is pretty good, right? And we find a very good linear relationship, and it's very strong linear relationship, right? But when kids grow, when they're young, they grow fast like this. But what if they're getting older? What will be the reality? The reality is the people is not going to grow as fast afterwards. The slope will change, right? And then when you get old enough, sometimes, most commonly, you're going to see people drop weight, right? So this will be what's truly happening. But if you're predicting someone who's 60-year-old, you are basically extrapolating. You're saying the people will grow at the same rate until they're 60, right? And we know that's not right. And that's why the prediction is absurd. So extrapolation is to make prediction that's outside of your sample data range. So within the sample data range, if there is a linear relationship or not. We can see we have proof, right? But outside of the sample data range, we don't know what's happening. We don't know any information about it. You can't just assume the linear relationship will continue, right? So extrapolation can be risky sometimes. We need to be careful. It's always safe to predict within the sample data range, but it may not be safe to predict outside of the sample data range. Extrapolation, right? Extrapolation is risky, but it doesn't mean we can't do it, because most of the study, we want to focus on, predicting the future. So if you have a business, you want to see how your business will be next year or next 10 years, right? So you want to predict the future. Anytime when you make predictions about the future, you're making extrapolations because you don't have future data unless you do time traveling, right? But, that's not the case. So please be careful about extrapolation. It doesn't mean you can't do it, but anytime when you make extrapolations, make sure if that assumption will be reasonable. Is it reasonable to assume the trend will continue outside of the data range where you're trying to predict, right? Okay. So then, next, before you do regression, please always try to get a good habit of making a scatter plot. You can always just go ahead and do the calculations to find the slope intercept, but if you don't do a scatter plot, sometimes you're going to miss something very important. So for example, if the scatter plot tell you have a very good linear relationship, that will be a good indicator that you can do a simple linear regression, right? Because we observe the linear relationship. So we can do a linear regression. And if the scatter plot shows you outliers, you have to be careful because regression slope and intercept you calculated, they are not resistant either. So outlier will affect the slope and intercept for just that one individual. And most of the time, outlier are data errors. You need to fix them or delete them, right? So if you don't look at the scatter plot, you're not gonna be able to observe the outliers, okay? So please make a scatter plot. And then another thing is, sometimes you're gonna get a regression line. You can still get an equation, but it doesn't fit very well. But making a scatter plot, you can see if the relationship is obviously not a linear relationship, like in both of the cases, they're non-linear relationship, right? So then you don't have to do a linear regression. You can do a non-linear regression. But that's not what we're going to cover, but we need to know if we want to do a linear regression, make sure you have a linear relationship, right? Okay. So then this is the first animal for attendance check, and this is hippopotamus. Right. So then how do we find a regression equation? We know the general form of regression equation is y equal to intercept plus slope times x, y equal to mx plus b, right? So with the least square method, we can calculate the slope and intercept using the formulas provided here. So B1 is a fraction of two summations, okay? This should have been xi minus x bar. I think I was being sloppy. I didn't put the indexes, but it should, it's just compared to the notes before. This should be xi minus x bar. I should be subscript yi minus y bar. Let me see if you can fix this very quick. Maybe you can copy it from the Word file. We need to have that summation function. I didn't copy it at all. Okay. Okay. And then the other one is sum of xi minus x bar, yi minus y bar. All right. This is not something big, but it will be better if it's fixed. Okay, so this is the formula to calculate B1. And then once you calculate B1, you can calculate the B0 after, right? So always calculate the slope first and then intercept. And B0 is y bar minus B1 times x bar. So y bar, x bar, they are sample mean, right? Sample mean for variable x and sample mean for variable y. So once you have B1 and B0 calculated, bring it back to the regression equation. You have, you have the regression equation established. So basically bring back to the general form. For example, if B1 equal to -5 through calculation and B0 equal to 3.6, then we can see the regression equation is y equal to B0 plus B1 -5 times x, right? So that's a regression equation if that's the case. So don't forget to write into this form. All right, so earlier I mentioned a measure to tell how well the model fits the data, coefficients of determinants. It's also called R square, right? R square is basically calculated by correlation R, take a square. Since correlation is between -1 and +1, correlation square will be between 0 and +1, right? And since it's between 0 and 1, it's like, a percentage thing, right? From 0% to 100%. So we can convert this number into a percentage and indicate what percent of the variability in the data is explained by the regression equation. So for example, if R equal to 0.8, R squared will equal to 0.64, we convert 0.64 into 60%. We say 60% of the variability in the data is explained by the regression equation. So that will tell you how well the model fits, how well the equation explains the data. The highest is 100%, right? So basically in R equal to 1, when all the points are perfectly aligned in the the linear form. So that's 100%. There's no deviation. It's perfect. But if the points are not perfectly on a proposed form, then it's not 100% anymore. It's going to drop, to 90%, to 80%. So the higher the R square, the better model you're getting. So anytime when you do a simple linear regression, you want to have a high R square value. That will tell you, your model is good. If R square is low, like you only got 30% or 40%, then your model is not good. So maybe you should look for other models. Okay. Right. So now let's look at an example. How do we find the regression equation, right? So we're going to have these formulas copied over, and we're going to work on a small example as what we did earlier. So before, we use this same data set to calculate correlation, right? If you recall, we can find the sum of xi minus x bar, yi minus y bar. That will be the column total here, right? That's 44. And then the correlation calculation is this. Then the top is 44, and there's 5. And then you just need to find the standard deviation of x and standard deviation of y. And each of the standard deviation will be the corresponding sum of the square columns, right? So sum of xi minus x bar square is 40. And from here, we can calculate standard deviation of x, 3.16. And then sum of yi minus y bar square is 50. So we can calculate standard deviation of y is 3.53. Then we plug everything in, we can calculate the correlation. So that's what we did in the last class. So now, if we want to find the regression equation for the data set, between the two variables, we can use the same worksheet to get it, right? So for example, the 3-column total that we have up here is 40, 50, and 44, but you need to understand 40 is sum of xi minus x bar square. 50 is sum of yi minus y bar square, and 44 is sum of xi minus x bar, yi minus y bar, right? If you understand that relationship, and we don't need this, finding the regression equation is very easy. When you look at regression equation, B1 is this. So then basically you just have two numbers. The top is 44, right? And the bottom is 40, right? So that will equal to 1.1. That's B1. What will be 0? Intercept. So B0 is y bar minus B1 times x bar. So what is y bar? Y bar is right here, right? 8. What is B1? 1.1. What is x bar? X bar is 5. So we calculate, right? So 8 minus 5.5 is 2.5, right? So the regression equation is B0, oh, y, don't forget, y equal to B0 plus B1 times x, right? So this is a regression equation. It's pretty simple, right? So once you find a regression equation, then people will ask you what percent of the variability in the data is explained by the regression equation. So what they're looking for? Coefficient of determinants, right? It's R squared. And we know correlation R take a square will be simply R squared. That's where the name comes from, right? Correlation R take a square. And we learned about the correlation, right? Correlation is this. We need to take a square of it. So then we can calculate. So 0.972. So you can answer about 97.2% of the variability in the data is explained by the regression equation. And that's it. Right? Okay, so we can verify this very quick using the software as well. So for example, you bring the data into Excel, you have X, you have Y, right? So first we can make a scatter plot. So we can find a scatter plot. So this is X, this is Y, right? And then once you click on the form, any point, it will highlight the entire form. So you can do add a trend line. So basically that's adding a regression line. You have some options here. So you can do nonlinear regression, all different kind of regression process, but we're only gonna look to the linear regression because we wanna see if they're, just wanna study the linear relationship. So then you can display the equation, display the R square, and it can compare to our numbers, right? Intercept 2.5, slope 1.1, R square 0.968, and that matches with our numbers, right? R square is a little off because we have rounding errors. Okay. All right. So then when you have that equation established, then for any given x, it can predict y. For any given y, it can predict x. And that's about it, that what you do for, regression process. You find a regression equation, you find R square, you do predictions, and then watch out for extrapolations. Okay. So let's look at example again. So this is the same study at background as what we see in chapter 4, scatter plot and correlation. But here we're going to do regression process instead of correlation process, right? So a study looked at the relationship between the knee height and overall body height of 6 adults, and the data are shown below in centimeters, the same data set. So make a scatter plot and examine the main features, right? So you have a scatter plot of 6 points, and you can look at the form. It's a linear form, direction, positive, strength. And we kind of ask you guys to estimate last class, right? It's actually a pretty strong relationship with correlation 0.89, right? So it's a strong relationship. And there doesn't seem to have outliers, right? So there's no extreme points. All the deviations are kind of, comparable. Then find the least square regression equation. Y equal to B0 plus B1 times X. So we need to find the regression slope and intercept from the data set. So we can make the similar worksheet like what we did earlier, right? So you need to look at the last 3 column totals. This one is xi minus x bar square. So sum of xi minus x bar square is 181.84. Then sum of xi minus x bar, y minus y bar, that will be this column total, right? So then if you want to do regression, it's pretty simple. You're going to use this summation, sum of xi minus x bar, y minus y bar divided by summation of xi minus x bar squared. That's our equation right here, right? So this is another equation for slope, but we're not going to use it. We're going to just use this to be, just less confusing. You can do it the other way, but, some people get confused. So then B1 equal to the ratio of the two numbers is 2.45. And the B0 is y bar minus B1 times x bar. And y bar is right here, 166.9. X bar is right here, 50.5, right? Just plugged it in. And B1 is 2.45, we just calculated. And that'll be 43.175. So the least square regression equation is y equal to slope 43.175 plus, intercept 43.175 plus slope times x. Slope is 2.45. So this is our regression equation. And then the next question is asking, what percent of the variability in the data is explained by the least square regression line? So basically, you need to find R square. So this is the same replicate work we did in chapter 4 to calculate the correlation. And after that, just calculate R square, right? R square is correlation. R take a square, about 79.2% of the variability in the data is explained by the regression equation. Okay. So if you like to verify, we can verify these in Excel as well. So if we copy these into Excel. So I'm gonna put them over here. Then just like what we did earlier, we're gonna make a scatter plot. So the scatter plot by default, they're gonna start with 0. But when they do that, but on both X and Y, when they do that, you can see all the points are kind of use a little corner of the XY plane, and that's not obvious to look at the trend. It's hard to look at the trend when all the points are clustered together. If you want to make it more spread, you just need to adjust the axes. So for example, for y-axis, there's nothing below 100, right? So right click on that and format axes. And then here you can choose what's the minimum, what's the maximum. For example, there's nothing below 100. We can start from 100 instead. So, it's better, right? And then for X, the same thing. You can see there's nothing below 40, right? If you format X-axis and start from 40 instead. So that way you can see, the scatter patterns is very easy to observe. So now if you click on the points and add trend line and then display equation, display R square, these are what we do, right? So slope is 2.45, intercept is 42.9, R square is 0.7921, right? So that's very close to what we have. We have rounding errors. Another example, here are the average monthly temperatures for Chicago, Illinois. In this table, months are coded in integers with January corresponding to 1 and February is 2 and so on. So July is 7, right? So plot the data with months on X and temperature on Y, describe the relationship. So the relationship is pretty good linear relationship, right? So it's the form is linear, direction is positive, strength is pretty strong. Outlier, it doesn't seem to have outliers, right? So then if that's the case, we do have a very good linear relationship. We should be able to do a regression process, right? So you can find a regression equation. So the same process, find the regression equation, make the worksheet. So you find the slope 9.45 and intercept 9.8, right? So the slope is 9.45. I ask you to explain the slope in terms of the context words. How do you explain it? 9.45, what does it mean? Rise over run, right? But in context words. So for a year starting in January, when you go over 1 month later, the temperature will rise 9.45 degree, right? Okay. So you don't have to use the exact words, but make sure you explain using the context words instead of a general term, or apply to anything we ask. If I ask to use context words, do not use general term. So you need to basically, that will kind of test if you really understood what it is, or just simply memorizing the terms, right? Okay. So next question is, can you do some predictions then? If it is December in Chicago, what would it predict the temperature to be? And December, we know if you buy the coding, December will be 12, right? So then for the regression equation, we find X will equal to 12. And when you do that, the temperature in December will be 123 degrees. Does it make sense? Of course not, right? December in Chicago, it should be very, very cold instead of this, crazy hot, right? So what's going on in there? It's another extrapolation, right? Your sample data range only cover from January to July. You don't know what's the temperature gonna be, but you assumed it will keep rising, right? But we know in reality, the temperature will actually start to fall, right? So again, always be careful about extrapolation. It could be risky, but it doesn't mean you can't use it. You could still use it, right? Right, so this is the second animal for the attendance check. This is the butterfly. Okay, and this is the last practice, I think. Speed kills MPG, and everyone drive cars, right? When you drive on freeway, when you go long distance travel, what is the best speed if you want to save gas? If you want to save time, you drive high speed, right? But when you drive fast, does it mean you're going to save gas for the same distance you travel? Not necessarily, right? So what's the relationship between the speed and the fuel efficiencies for cars? So here's a study. They have 6 brand new Toyota Camrys are selected to test drive on the freeway with different speed, and they drive for 20 minutes. And the data collected is below. So when you drive 50 miles per hour, the MPG value will be 35. And 60 miles per hour, it will be increased to 38. But when you go to 70 miles per hour, will decrease to 30. And then when speed is 80, the MPG will be even lower, 24. When speed is 90, it become 20. When speed is 100, it become 18, right? So we know there is a relationship between the speed and MPG values. Then what is that relationship? And of course, we can describe it. We can use a graph to describe it, and that's scatter plot, right? So the scatter plot shows a very good negative, strong linear relationship, right? negative, strong linear relationship. And there doesn't seem to have outliers. Next, find a regression equation to fit the data. So again, you need to make a worksheet. I'm not going to require you guys to make a worksheet like this in the exam. I think not even on the homework. I will give you the majority of the worksheet done, but we'll leave maybe 1 line or 2 line blank. So as long as you understand how this works, give you enough time, you should be able to replicate the work. So I'm not going to focus on, all the tedious calculations, but I want you to understand how everything works out. And most importantly, after you calculated the column total, you need to realize the column total is always a summation of the corresponding column title, right? So then if you realize sum of xi minus x bar square equal to 1750, comparing the title, and the sum of xi minus x bar yi minus y bar equal to negative 725 right here, right? So then the slope is simply the ratio of these two will be negative 0.41. And intercept B0 will be, y bar is right here, 27.5, minus B1. So you have minus, this is from the equation, right? And B1 is a negative number, right? So please be careful watching the signs. This is the most common error I see when students, trying to do the calculations here. Always the sign, right? So then negative, it becomes positive. You're gonna add those numbers together. So it's 58.25. The least square regression equation will be y equal to b0 plus b1 times x, right? So plus b1 times x, but the b1 is negative, the slope will be negative, right? Okay. So then, according to the regression line, what MPG value will be brand new Toyota Camry have if you drive at 70 miles per hour? So when you drive at different speed, okay, estimate their MPG values. Of course, 75 is within the sample data range, right? It's safe to predict. So just put 75 into x into the equation, right? So for this, x will replace by 75, we can calculate. It's about 27.5 miles per gallon, right? And the next one, according to the regression line, if a brand new Toyota Camry has MPG value of 32 on freeway, how fast do you think he's driving? So we're given MPG as y is given, right? When y is given, we try to find x. We're going to put 32 into y, right? And you have x as unknown. We solve it. It's about 64 miles per gallon, right? Okay, and the last question, what percent of the variability in the data is explained by the regression equation? So we're looking for R square, right? Anyone recall the formal name of R square? I wouldn't even know if I don't teach the class. It's called coefficients of determination or coefficients of determinants, right? But R square is fair enough. R square, we need to calculate R correlation and take a square, right? It's a 0.9216. Okay, again, if you want to verify this using softwares, you're welcome to do so when you do homeworks to make sure your calculation is correct. But we don't require software in a class, so everything needs to be manual because it's hard to require everyone have softwares access. Okay, so we make a scatter plot just like what we did earlier, right? So again, if you want to format the axis to center all the scatter points, so there's nothing before 40. And then y, there's nothing below 10, right? So this way, it's pretty good centralized. So if you want to get a regression equation, click on any points, right click, and add trend line. And then on the bottom, display equation, display R squared. So you can compare with the numbers we have. 0.4143 as a slope, negative. So there's a negative sign here. And the intercept is 58.57. You know, we got negative 0.41 and 58.25. That's close enough. And R squared, we got 0.9216, and they got 0.9061. You know, that's close enough as well, you know, considering the rounding errors. Right, so this is a regression process. Basically, all the questions here that will involve all the possible questions that people ask for regression. Okay. All right, so this will be it for this chapter. Send me questions. And you can join the office hours if you needed to. Thank you very much.